My name is Evan Sun. I'm a senior quantums applications engineer at Riverlane. I'm going to go through a little bit of what we've done here, why it is important, how it actually works, and then finally get to the actual live demo. We have integrated our Deltaflow 2 quantum error correction stack with Quantum Machine's OPX 1000. Now, important. In order to get to fault-tolerant quantum computing, we need real-time error correction. And there are two key metrics that we care about here for this error correction. The first one is the logical error probability that basically says, okay, how often do you actually get an error on your logical qubit? The second one we care about is latency. We need to get the result back and determine whether an error has occurred as fast as possible to enable real-time decision-making and logical branching using our QEC system. So let's go through exactly what we're going to be doing here today. We're running a quantum memory experiment, which essentially says we have this logical qubit at the beginning of the experiment, and we want to keep track of its state throughout the entire experiment. How is this exactly going to work? So this is where we go into the user flow. So from Quantum Machine's OPX 1000, we first have a C++ program. Like Yaniv said, this is where you're going to select what type of decoder and accelerator you want to use. In our case, we're using the Deltaflow 2 system. Second, you're going to define the Deltaflow configuration. There are multiple code distances that we can use to enable quantum error correction. The higher the code distance, the less likely you have a logical error. However, that does mean you're using more physical qubits. All of that is compiled, and that's sent over to the Deltaflow 2 quantum error correction stack before the experiment has begun. Now, this is where we get into the real interesting stuff. It's the actual running of the experiment. During the experiment, the OPX 1000 will be sending readout packets to our Deltaflow 2 system. The Deltaflow 2 system is constantly looking at those readout packets and determining if any errors have occurred. At the end of the experiment, the OPX 1000 will ask, oh, has an error occurred? And the Deltaflow 2 system will give it back the final corrected observable result of the logical qubit. What is actually happening on the Deltaflow system? Well, during all the time that the readout data is being processed in real time, it is measuring it is calculating, and it is finally decoding what the actual error probabilities are. Now we're going to go into the actual demo, which I'm sure you all are excited to see. So as you see here, it's very easy to configure. We have a distance, 3, 5, 7, 9, or 11, and the number of shots that we want to run. So for this, let's start with the distance 5 code, and let's see what our logical error probability is. Right now, this is talking to the OPX system, telling it which configuration to send to the Deltaflow system. And finally, as you can see here, we actually just ran all 1,000 shots. And this is what our final results were. Out of the 1,000 shots that we ran at a D5 distance, we had 40 logical errors and 960 successful shots. So what you probably want to know is, okay, without error correction, that would have been a 22% error rate. With error correction, we only have a 4% error rate, which seems pretty good. Let's see what it looks like plotted on our graphs here. So this is a graph with all of our prior measurements that were taken before we did this real-time demo. So you can see at the different distances with 50,000 shots what our logical error rate was. Now, the light green is what our logical error rate of the live demo just was with 1,000 shots, and the red dot is what it would look like without error correction. You can clearly see how much better our logical error rate is when we have error correction. And this is our latency plot that we were just discussing. Like I said, it's really important that we have a low latency so that we can enable real-time decision-making by the quantum controller, in this case, the OPX 1000. Right here, you see this green, the bright green dot is what our real-time experiment measured as far as latency goes, and the latency measurements are plotted for all 50,000 shots for the other distances that we've done. You also see here 2 lines, and you're probably wondering what is the importance of these 2 lines. Industry believes that 10 microseconds is the latency number that we are trying to hit in order to enable useful fault-tolerant quantum computing. Currently, Riverlane's target is 20 microseconds, obviously with the goal of getting down to 10 microseconds. But you can see that across all 5 code distances, we still are well below the 20 microsecond goal that we have laid out for ourselves. So now we're going to run a D11 code. This is our largest code that we can support right now. And here you see what has changed. As you can clearly tell, not only has our logical rate decreased, we're now at 0.00 plus or minus 0.00, which essentially is a rounding error because of the number of shots that we're running. If you were to see the 50,000 shots, you would see the logical error probabilities that were plotted previously. But also note how high our logical error rate would be if we didn't have error correction. That's 50%. Essentially, it's a coin flip on whether you got it right. This just goes to show how increasing the distance is going to enable us to achieve fault-tolerant quantum computing sooner. And again, going back to our live plots here, well, it seems that the distance 3 code is still shown up there, but what you would see if you were able to see the distance 11 code in real time is that that dot would be very close to what we run with our 50,000 shots. As you can see, we've made a lot of progress here between Riverlane and quantum machines on enabling fault-tolerant quantum computing. We're hoping to increase this collaboration in the future and continue to work towards faster quantum computers. Thank you.